Hello students, my name is Gautam Das. This is the third part of the stability of carbocation class or video, whatever you said. I hope that you already subscribed my channel. Now, last class we have I have given you a general order where you have seen that this triphenyl methyl carbocation is the most stable so far as what we have done last class. Now we are going up one notch above. We are increasing the level, and we are going to discuss some extra stable carbocation. Let's first consider a much easier extra stable carbocation because whenever we are considering what effect is more effective in stabilizing the carbocation other than more than resonance effect, then it is called aromatic aromatic ring or quasi aromatic whenever the positive charge is on aromatic ring, and so and so. Now if we consider this one, suppose I'm calling it A, this is called tropylium ion or cycloheptatrinyl carbocation. Now this is aromatic, or you may say quasi aromatic because it has a positive charge on it. Aromatic. Now why it is aromatic and all these things that you already know, or if you don't know, we will discuss that in aromaticity chapter. But you can simply say all the carbon atoms are sp2, all the carbon atoms are sp2, so it's a cyclic conjugated polyene where all the carbon atoms are sp2. All the p orbitals are p orbitals are perpendicular to the plane and they are involved in conjugation. There are 4q plus 2 pi delocalized electrons where q is 0, 1, 2, 3. So it is satisfying all these other cyclic conjugated planar, all carbon atoms sp2. It's actually a 4q plus 2 pi because it is 6 pi electron system. So when q is 1, it is satisfied this, and it is totally delocalized. So it is aromatic. It's an aromatic ion actually, quasi aromatic or aromatic ion. There is a positive charge developed on aromatic ring, this quasi aromatic, and it has 7 equivalent resonating structure. Now I'm not going to draw the 7 equivalent structure at this level because that's a part of aromatic compounds and so on. So in some other videos or other class we'll discuss that. But what I'm going to mention is this is an extra stable carbocation. Why it is an extra stable carbocation? Now we have seen that triphenyl carbocation is highly stable. Tropylium ion is even more stable than triphenyl carbocation. Here there is a Plasser effect exerted by 3 phenyl groups. 3 phenyl groups. But still here there is aromatic ion which is quasi aromatic, more stable than this. So this is the first extra stable carbocation. Hopefully you have understood that thing. Remember, cycloheptatrinyl carbocation, tropylium carbocation is more stable than even triphenyl methyl carbocation. If you go back to that order which I've given in the last video or last class, so above that triphenyl carbocation there will be this. Now another extra stable carbocation which I am going to discuss. Now this you all know, but maybe you all know, but it may not be the reason you all know, but you know all these things, I think, because this is a very common question which comes, this or derivative of this. What is this? Is cyclopropyl methyl carbocation. This is more stable than benzyl carbocation. Sorry, this is more stable than benzyl carbocation. Not by much, but this is more stable than benzyl carbocation. Now, what is happening in this cyclopropyl methyl carbocation? Shortly we call it CPM, but I prefer the word cyclopropyl methyl carbocation, which is responsible for being extra stable carbocation. It's one of the most stable carbocation, and this will become relevant whenever I'm going to give some orders, which is quite important. This is for the higher level. Now I can simply say one thing. Before going into the details, you have to remember a few things. This is case of dancing resonance. We'll see what is that. Or sigma bond resonance. Here we'll come across something called sp5 hybridization, where around 16 to 70% is character. That means actually, if we break it down for your sake, this sp5 sigma bond is between between carbon and carbon in the ring. This carbon in the ring, while we have sp2 1s sigma bond between carbon of the ring and hydrogen. Now, if we draw it properly, I'm drawing here. Just give me some time for trying this. These are all observed facts, not something which is imaginary or hypothetical. These are the two hydrogen atoms I'm talking about, of the carbon of the ring attached to the carbon of the ring. Now, this is the, if we consider this one, this is the bent strained sigma bond system of cyclopropyl ring. Bent strained sigma bond, actually the banana type of bond. Here this is this interorbital bond angle is actually 102 degree, which gives us sp5 hybridization. This is sp4 sp5, this is sp4 sp5, and this is sp2 1s, and so and so. Then this is the overlapping. This bent strained sigma bond system of cyclopropyl ring overlaps with the vacant 2p orbital of this cyclopropyl methyl carbocation, making it highly stable. This is density resonance. Now the question may arise, how come sp5, carbon has only 3 or p orbitals? How come sp5? Now it can be mathematical, it can be simply deduced that actually it is using 3p orbitals and 1s orbitals in both forming sp5. If I consider this one, sp5 is what I am saying. This, suppose this is the ring I'm talking about. So this is the carbon. This sp5 is between this, and sp2 1s is between this hydrogen atom. Okay. like this. So here it can be simply proved by some mathematical formula. I'm not going to details, I'll just touch it, but I don't require so much details. You just have to require this thing. Now if we consider the dancing resonance, although I've seen some video in this YouTube only where they some of the so-called good teachers, great teachers have mentioned there is nothing called dancing resonance, but there is something called dancing resonance, and there is something called SP5 hybridization. Otherwise we cannot explain why this is highly stable, and that's why we cannot explain that why ring expansion does not occur whenever we do ring expansion, because although 4-member ring is more stable than 3-member ring, that we know that ring stability 4-member ring is more stable than 3-member ring, but still so dancing resonance is actually a fact. But I've seen some, I've just mentioned it because I've seen some videos where someone says that the dancing resonance is nothing called dancing resonance, or rubbish, if I may say term, may use the term, but I'm not going to use the term in this public video. Anyway, this I can easily prove that it is using actually 1s and 3p orbitals. Just formula. I will give you the formula. We can do it. Anyway, now this dancing resonance. If I consider this one, this del plus sigma bond resonance. Yeah, this is opening up. We are getting this, and suppose this is opening up, both are equivalent, then we'll get this. So the proposed structure will be something like this. This is this sigma bond. Proposed structure is like this. Proposed structure is like this, and which can be shown in this way. The 3 structures, and this is actually dancing resonance, or sigma 1 resonance, SP5. Now, why we are saying SP5? Just let me touch a bit, because I've seen a video where someone is saying there's nothing called SP5 and something like that. Now, if we consider a cyclopropane ring, whenever we are drawing like this, drawing like this, these are internuclear. This is carbon-carbon internuclear bond angle we are talking about. This is internuclear. If you actually talk about the interorbital angle, as I've shown there, interorbital bond angle, if I actually talk about this, there are hydrogen atoms. I'm not drawing this, simply hydrogen atoms. I'm considering simply like this, suppose, or let's consider this. Let's not confuse ourselves. Now, if I consider this one, now this internuclear bond angle is 60 degrees, no problem with that. But this interorbital bond angle is 120 degrees. One is 42 degrees, so 102 degrees. Sorry, this is 102 degrees. This is interorbital bond angle. Now, there are some simple mathematical things which you don't require actually, but I'm just saying it for the purpose of saying it. You don't serve you any purpose as such, even for JEE Advanced. If I say a SPA hybridization, there's one formula called A1 plus A cos alpha is equal to 0, where alpha is the interorbital bond angle. So if you put that A cos 102 degree to 0, here you will get A as around 4.8, which is A cannot be a fraction, so 5. And using this formula, if SPA hybridization, then S character is 1 plus A, and P character is given by A1 plus A. And considering that in this, whenever we are considering one particular carbon, suppose I am considering this one particular carbon, there are two sp5 and two sp2. Let's keep it cyclopropane only then. Okay, two sp2 which are forming two bonds with hydrogen atom. Here, by this simply applying this formula, we can actually show that actually 3p orbitals are being involved and 1s orbital is being involved. Anyway, it has nothing to do with your J, even for J advanced. This would be required. It's just I've shown because I've just come across just one heading or something like that. Someone has written or posted a video that there is nothing called dancing resonance or nothing called resonance. So ask them to explain why cyclopropyl methyl carbocation is so high stable, is the extra-stable carbocation. It's hydride. I've said this is a database thing. You have to know. It's actually hydride ion affinity is very high. It's an exothermic reaction. Even stable than see here, if you consider resonance, how can we make it more stable resonance? Now, one thing you have to keep in mind, obviously this does not mean that this will be stable. This does not mean this will be stable. This does not mean this will be stable. No, these are not stable. These are not stable. These are simple 1 degree carbon atom. For these two cases, there will be actually ring expansion, which we will try to cover in some other things. If I take one class for ring contraction, ring expansion, or shifting or rearrangement in carbocation. So these are not stable. This is typical for cyclopropyl methyl carbocation. This bent strained sigma bond system of cyclopropyl ring overlapping with the vacant 2p orbital of this carbon atom. This is typical of cyclopropyl ring, not other cyclic rings, cycloalkane rings. Okay, so one thing we have learned here that because of something known as dancing resonance, also called sigma bond resonance, this is even becoming more stable than benzyl carbocation. Now, why we have been discussing this? Obviously, for one thing that this thing which I've already mentioned is slightly more stable. But try to understand one thing: there is actual resonance of this dense resonance is more preferred than this. But this is more important because of another thing. We have discussed one thing which is cycloheptatrinyl carbocation and tropylium carbocation, which they are aromatic. Aromatic is highly stable because why aromatic compounds are highly stable? If you consider this, because they have actually completely filled. If you draw the pi-MO diagrams for them, it can be easily drawn by drawing the cyclic compound with one of the vertices point downwards. Then the relative energies of the pi-MOs correspond to the vertices. If you draw a straight line in the midpoint of the structure, the MOs below it, the pi-MOs below it are called bonding, above it is called anti-bonding, and any MOs at the cyclic structure which will come across in cyclobutadiene will be non-bonding. Now, for aromatic compounds, we have always completely filled MOs. For anti-aromatic compounds, we have half-filled MOs. That's why they are highly reactive or very unstable, even less stable than the corresponding open channel log. That we'll discuss in aromaticity chapter if I upload any video on aromaticity and so on. Now, the reason I am discussing is this. This is highly stable carbocation, and which we have already discussed this. This is even more stable than this. So, is this the most stable carbocation known to us? But there are a very large number of carbocation which are more stable carbocation than this. One such, if I can give. This is tricyclopropyl methyl carbocation. Tricyclopropyl methyl carbocation. That means dancing resonance from 3 sides. Dancing resonance from 3 sides. Highly stable. Highly stable. Even stable than aromatic, quasi aromatic with 7 equivalent resonating structure. This is more stable than this. Another order. These are very important for the exams purpose. Another order. This is obvious. This is obvious. You can simply say more dancing resonance. Dancing resonance is decreasing, so this order. So these are three very important things. This is a very important one. This is a very important one. A lot of people have confusion regarding this thing. So if you try to remember these 3, hopefully you have drawn these 3. Anyway, you have the video. You can pause it and draw it later on. Now we're almost at the end of the stability of the carbocations. Almost at the end. A few other things obviously I will give you for the questions, but not everything I will discuss. But the database things which you have to know, you cannot predict. I've already explained. Another thing, obviously, this is something which can be explained very simply. This is very simply we can explain. Suppose I've given you this. I've given you this. I've given you this. I've given you this. 1, 2, 3, 4. You are being asked to arrange them in order of decreasing stability. Now this is very easy compared to whatever we have done just now. And we have to just comparison between aromatic and aromatic. Now, if you consider this one, this we have already discussed. This is tropylium and cycloheptatriene, and we already know this is aromatic. Now, this is cyclopropenyl carbocation. This is another quasi aromatic compound. Another quasi aromatic compound. Another compound. Well, cyclic planar, then conjugated, isn't it? 2pi system, 2pi electron system is satisfying. That 4q plus 2 to the power q is 0. Satisfying this. So both these are aromatic and aromatic. And whenever we are saying a positive charge on the aromatic compound, then we call it also quasi aromatic. Same thing. Anyway, so both are this aromatic, but these have 7 resonating structure, equivalent resonating structure. This has 3 equivalent resonating structure. I'm not drawing these structures here because that will, if we do another class on our video on aromaticity and compare between aromaticity and non-aromatic, then there we'll discuss that. Now, if we consider this one, what is the difference of non-aromatic compounds? Cyclic or acyclic systems that are non-planar. That are non-planar. That are non-aromatic. Aromatic, I've already said. Aromatic characteristics should have some properties, like it should be a planar conjugated cyclic polyene with 4q plus 2pi delocalized electron where q is 0, 1, 2, 3, etc. All the ring atoms, it may be carbon, nitrogen, oxygen, sulfur, because we are considering also heterocyclic compounds, suppose, must be sp2 hybridized. All the ring atom must have a p orbital available for the cyclic overlap, and so and so. And another thing which we also should add, that such compounds, aromatic compounds, undergo electrophilic substitution in preference to addition reaction. With addition reaction, aromaticity is actually lost, and they have high resonance energy, obviously. Now, antiaromatic compounds are this, again, cyclic conjugated polyenes, cyclic conjugated planar polyenes. Till now, it is similar to aromatic, but it contains 4q pi electrons, and that are less stable than the Ropen chain analogs. Anti-aromatic compounds are not only less stable than aromatic compounds, but also less stable than Ropen chain analog. If I go a little bit little out of track, if I consider this one and this one, stability, 2 will be more stable than 1. This is aromatic, 3 covalent resonance, but this is open chain compound. But if I consider this one and this one, this is anti-aromatic. Anti-aromatic, this is open chain. Stability order, this, if I say 1, 2, here stability order will be 1 greater than 2. Stability order. So anti-aromatic compounds are cyclic, planar, conjugatable with 4q payload that are less stable than the open chain. They are not only less stable than their aromatic counterparts, but also less stable than the open chain analog. This can be simply explained. This portion can be simply explained with the help of MO theory. That will we may discuss in one of our other classes if we discuss aromaticity in details. Now, if I think of this is sp3, this is sp3. These two carbon atoms are sp3, so this is non-aromatic. And if you consider this carbon, cyclic, planar, conjugated, all carbon, this is sp2 carbon, all carbon, all these carbon atoms are sp2, all these carbon atoms are sp2, while these two are sp3. This is sp2 obviously. So this is non-aromatic, where this is satisfy these 4 pi electrons. So it is satisfying 4q pi electron system. So this is anti-aromatic. Now we know that the basics of the starting point of aromatic chemistry, the decreasing order of stability. Non-aromatic, what we have said, it may be cyclic or acyclic system that are non-planar and non-aromatic. Decreasing order of stability is aromatic. Greater than, I'm saying is non-aromatic, anti-aromatic. I mentioned like this: non-aromatic greater than anti-aromatic. A is anti-aromatic, N is non-aromatic. So now these are two aromatic ion, quasi aromatic ion, but this with 7 equal resonance structure, this with 3. So 1 stability order, 1 greater than 2. Then comes non-aromatic, which is 3. Then comes 4. This is 4, which is anti-aromatic. This is a simple one. This can be explained. You don't have to actually note the facts. This you can explain from the aromatic concept. Now, let's say that some example of carbocation which won't exist. Well, they won't exist at all. We have seen that vinyl, phenyl, ethanol, so far whatever we have discussed, the ethanyl or alkanyl carbocation are least stable, we say, but they may exist, but quite very unstable. But if I say this type of thing, I can simply say this does not exist. Now there is a rule, and before going into the rule, if I say one thing, that this is what Bredt carbon atom. I hope you all know this thing: Bredt system, fuse system. I think IUPAC system. If even if the IUPAC, if you have done for JEE advanced level, you must have done the IUPAC for bicyclo compounds or spido compounds. That's in actually the syllabus. If you have not done, you should join my classes, which details are given there. No, I'm just joking. You may or may not. Anyway, now. The Bredt, these are Bredt carbon atoms. The Bredt carbon atom cannot assume coplanarity because of the steric requirements of the bridge ring structure. A little bit difficult. If I say like this, if I say the rule, it will be much easier. The Bredt carbon atom cannot assume coplanarity because of some steric requirements of the bridge ring structure. It is very simple. If you consider it, if I break up this, if it has to become coplanar, or then it has to be sp2. Let's just mark it. Mark the carbon atom. Suppose this carbon atom is A, this is B, this is D, this is C. Coplanar sp2 carbon means this AE bond, AB bond, and AD bond all lie in the same plane. What does it mean? It means both these rings are actually in the same plane. High strain. There's a high strain. I'm just trying to imagine two rings. I'm trying to when I just form two rings in one plane. This was very unstable. We can say it does not exist as such. This is actually put forward in some things called Bredt's rule. If you remember Bredt, so that will be helpful. It's very important for JER. This carbocation, if I want stability wise, we have seen that alkynyl, so far whatever we do, alkynyl carbocation is least stable. This actually does not exist, but even if they ask you stability, this is even less stable than this. Because the Bredt's rule says that the bridgehead carbon in Bredt system, remember this, Bredt system cannot be sp2 hybridized till one of the later part, the last part, whatever I mentioned, most of you don't know, till one of the ring size is 8-membered ring. Then it can exist, because 8-membered ring, that strain becomes much less, so it can exist in the same plane. One of the ring size is an 8-membered ring. Bridgehead carbon atom Bredt system cannot be sp2 hybridized till one of the ring size is 8-membered ring. Knowing this thing, we have already seen that this does not exist. Although this is not part of carbocation, but will this exist? Just check whether this will exist, whether this will exist, which one of these will exist, whether this will exist, whether this will exist. Let's check this one. For this again, the bridgehead carbon atom is sp2 hybridized, it does not exist. These are not bridgehead carbon atom, so it does exist. This is again bridgehead, not bridgehead carbon atom, so this will exist. Now this is what a carbanion, that means this is sp3, non-planar, so that state requirements is not highly strained, so this will exist. Now suppose I have given you this, or have I given you this and asked whether they will exist. Both of them will exist because they are fused ring, they are fused system, not Bredt system. They are fused system. So here this and this will exist. This is for Bredt system, not for fused system. Okay, these are fused system, these are Bredt system. And obviously let's try to draw this. If you consider this one, 1, 2, 3, 4, 5, 6, 7, 8. One of the ring is 8, so this will exist. But this can be sp2 hybridized. It's quite, the ring is so large, 8-membered ring, so it's quite large. Similarly, similar consideration. 1, 2, 3, 4, 5, 6, 7, 8. This will exist. So I think stability of carbocation part is quite covered. Maybe in some other classes I will give, we'll start a few things, but I will give you some questions to answer. There may be large number of questions which can be answered, which we'll discuss in later classes. Okay. So subscribe my channel, and if you like the video, please press the like button. And obviously, if you really want to go for JEE Mains and JEE Advanced and NEET, and not just say I'm going for it, 90,000 or 1 lakh students are just sitting for class. Anyway, those are all. Anyway, I'm not going to do that. So you can contact me, leave a message in the WhatsApp, and I can send you a message when to call back, and we can do offline classes if you stay in Kolkata. If you're not staying in Kolkata, we can do online classes. Also, obviously, for on Kolkata students also, online classes are available, and I only form very small batches. Anyway, thank you. Good night.